This conference will now be recorded.
Okay, so like I said before, my name is Ron Soto, and I am the co-founder of HackMiami and Pacific Hackers, and I also host these meetups. Uh, Today, we're gonna have a talk about building out SIEM with Elastic. I am familiar with the Elastic stack. It's something very important and very popular, particularly in startups. I have a couple of announcements to make. One of them is that on our next meeting on the 21st, we're going to go back to the library. Finally, we were able to secure a spot in the Broward main library. So we're going to be back on May 21st from 4 to 6 p.m. I will be speaking that day on OWASP top 10, and I'm hoping to make it as hands-on as possible. We're gonna continue with hybrid meetings since it's been requested that we continue doing this. Um, Today as well, after the this meeting, there will be a meetup, a in-person meetup at the Aventura Mall uh, food court. As you can see here, here's the details. You can actually check them out in the meetup page. And there will be some in-person meetup at the Aventura Mall around 6:30. So for those who want to meet other members of HackMiami, you can do that. Or also you can uh, see us on May 21st, and we're going to have a hands-on presentation of OWASP Top 10 API. We are starting to ramp up to prepare for DEF CON. If you're not in Discord, I suggest you to join. If you need the link to join, please text it in the chat and I'll send it back to you. We're preparing basically for two main conferences or three main conferences. One is RSA, which is in June, where we're gonna part of our staff will be running the Dark Arts Village in RSA. We'll be teaching a class in RSA, and we'll be hosting Capture the Flags and workshops at RSA, mostly the Pacific Hackers crew. We also are preparing for DEF CON as well. We have, remember last year we won the Black Badge and Capture the Packet. So we're gonna do an event to get you ready and prepare you for DEF CON. If you're trying to make plans, it's better to join Discord and try to find like-minded people that are going in case you need orientation or you need some sort of direction and which way you wanna or how long you wanna stay, where you wanna go, etc. And then finally, for those who attend both meetups, we have actually a very, very cool thing happening on May 13th in Palo Alto, California, where we're going to have the Pacific Hackers OWASP Bay Area mini con. We're going to have a mini con in Palo Alto. And then you have Marco, you have Irvin, and you have most of the crew from Pacific Hackers, which is a sister meetup. Um, and if you're in the Bay Area or you will be around the Bay Area during that time, there will be an actual presentation by GitHub itself, the GitHub security people, and all kinds of good stuff. You can check it out. There's going to be a video broadcasting. We will notify as soon as we have it. But if you are in the Bay Area, I would suggest you to attend it because we're trying to get ready to bring back the conference in the Bay Area, which will probably be at the end of the year. We haven't made a call yet, but we'll probably bring it back. And with that, then let's get on to today's presentation. Today, we're going to have a presentation about building a SIEM using Elastic. Like I said before, I am a very familiar with this. I worked at two startups which were based on Elastic stack, and this is something that, in my opinion, is very fundamental for centrally logging events and using it for security purposes. So with that in mind, I'm gonna have Mehdi introduce himself. I'm going to set you up as presenter.
So JT is going to go first. He's doing the Elastic, and then I'm doing the second part, which is the introduction to TLA plus.
Oh, okay, cool. I only see J. Is it J only? Yeah, there you are. So now I'm gonna make you a presenter. There you go. And then you can take it from here, man. The floor is yours.
All right, awesome. Let me share my screen. Okay. So hopefully everyone can see the screen. So this is going to be maybe a little bit shorter than I had wanted it to. I was going to include kind of a demo with this talk, but my machine doesn't have enough RAM for what I was trying to do. But nevertheless, we will drive through with the slides, and hopefully everyone is able to get something out of it. So yeah, my name is JT, and we're going to be talking about some additional Elastic features that you can utilize whenever you're trying to build out your security operation center, your SIEM, and just making sure that you can correlate and log events as appropriate. You know, there's a lot of different tools out there that you can utilize for these purposes, and lucky for us that they exist. Elastic is one of those tools. It does require a little bit of configuration and optimization to be completely useful for our purposes, but this talk will go into some of those optimizations that you can make. So just a little bit about me. So I'm a security engineer with a focus on security operations primarily. I had previously worked as a software engineer doing .NET development, also a little bit of embedded integrating with some of our building management system devices that we were developing. And this was about 12 years ago, and at least at the time, we put absolutely no focus on security whatsoever. So, you know, it'd be probably an interesting area of research for someone to look into on the current state of building management systems and whether, you know, security has kind of been added on since then, since over the last 10 years, you know, we've seen numerous attacks on infrastructure, on IoT. So it'd be interesting to see what that current state of the art is. Also had a background as a network engineer, doing your basic, you know, Cisco, Windows stuff. Spent a few years as a data analyst, and that was when I first got introduced to, you know, analyzing large quantities of data. You know, that was the first time I had actually just, you know, had to sit there and look at data as it was coming across the wire, looking for specific events. And so that kind of carried over like a natural progression into, yeah, natural progression with you know, transitioning over into a security mindset as well, because you really can't make security decisions unless you understand your data. Then I also did some IRT work, working with globally distributed teams and responding to various events, industrial engineer or infrastructure planner. So kind of been all over the place. And yeah, this picture was a throwback to the conference of 2016. I think it's 2016. It was a good time. Really looking forward to getting back in person with some conferences and get-togethers as well, as I'm sure we all are. So I wanted to include this kind of description because so when I was working as a data analyst, I was specifically looking at satellite data, and we were doing some remote sensing work. And you know, the flow, the execution flow of whenever you're developing remote sensing and trying to look for pieces of data that come across the wire in that sense is, you know, you develop your sensor, and that's where you're going to spend the majority of your time. You have to make sure that the sensor is operating appropriately, because, you know, if you're putting that particular sensor on a remote system, you know, in my case it was a satellite system, the hardware had to be correct before it went out into the field, because you don't really get a chance to do over on the hardware. And then also at the same time, you need to make sure that those triggers are established very effectively. because while that may require like a firmware update, for instance, it's not necessarily easy to do. And then you can spend some time on the analytics, but whenever I was doing this data analysis on lots and lots of data, my first time really experiencing big data, that was the execution flow, and it was very heavily upfront kind of cost in terms of effort that we were trying to do. Most of the time you're spending the bulk of your time on analytics, but in our case it was upfront. But computer networks, if you're looking at monitoring more of a traditional type of network where you actually have the ability to go in and make configuration changes on the fly, it allows for a more even distribution, so you don't necessarily have to spend so much time on developing of the sensor, because based on the outputs in your analytics, you can always go back and make those configuration changes. Now that's not universally true. There are instances where maybe you do have some devices on your network that are harder to update and make those configuration changes, but in a sense it allows that kind of loop back development cycle. But it does kind of follow a similar type of flow, sensor, trigger, analytics, but as I mentioned, you can always kind of go back and readdress those. But it's still regardless important to get that right, because we're trying to avoid this situation, right? We're trying to avoid the situation where we get alerts and we can't do anything with them because there's either not enough information or we weren't collecting the right information. So when I was working incident response, there'd be a lot of times where because it's a globally distributed team, I'd have to go and work with the local kind of SOC and incident responders and ask them, okay, what did you actually collect? We received this notification, we received an alert. So what information additionally can you provide to that? And a lot of times they weren't logging appropriately, and so we didn't have any correlating data. So as an incident responder, or especially as a threat hunter, it's hard to make that deterministic judgment of whether or not something is actually an event of interest and it needs to be identified further, or if it was just just a one-off, like something that slipped through. The difference between just getting a commonly used Trojan, for instance, through like a phishing email versus an active campaign against your network. So the correlation piece, it's what's really big whenever you're trying to make these determinations. So in that sense, we want to make sure that we do spend enough time in our initial design, but at the same time, if we need to go back and change it, we need to be able to do that as well. Okay. All right, so like I had indicated, this talk is going to be more focused on the optimization piece of Elastic, kind of once you've already had an initial setup of your ELK stack. We're going to do some of the architectural considerations for how you should develop your clusters for enterprise environments. This will include, how to design your node requirements for running our instances of Elasticsearch, configuration of our ingestion nodes, and then how data is going to be shipped to your clusters for further processing. And then as part of that pipeline, developing and standardizing those data nodes for storing and archiving the data once you collected it for search later on. I'm going to spend some time going over some various log sources that can help you identify specific logs that you may want to collect in your environment. And then once you have an enterprise architecture established, you're going to want to ingest those data from the log sources to the point where you can have that capability and leverage it for further threat hunting. So we'll cover how you can make quick use of this data for conducting that threat hunting. And with Elastic especially, that's really where the power lies. Its search capability is phenomenal. It's very, once it's set up, it's very intuitive to use, but it's not so intuitive to actually optimize. And so that's going to be the challenge for folks that are trying to implement it in their environments. We're not going to conduct a short walkthrough of these features because of the RAM issues I ran into, but we'll definitely leave here with some key takeaways for you all, so that way you have a good idea of at least where to get started whenever you're trying to implement this. So even though I said we're not going to go into the fundamentals of Elastic too much, I did want to show you just a review of the core components of the product. And if you do want to get an idea of how to establish and set up like an initial ELK stack for your use, there was a talk given by a previous HackMiami participant a couple of years ago that you can find on the HackMiami YouTube page, and he did a great job just going through how to set this up initially. But our primary components with ELK, the Elastic stack, are going to be the Elastic search engine, which is what really powers our stack, and it has the ability to search any type of document that's indexed. And then from that capability, it allows you to divide that data into indices and distribute it over your architecture, since Elastic is distributed by nature. And then it has a great auto rebalancing feature that you can utilize on the back end. I mean, it takes care of everything for you essentially. Now, if you do run into some issues with data balancing, there are manual ways to fix those issues. But it's going to require you to have a firm understanding of how your cluster is operating, so you can fully resolve any of those issues that pop up. And then we have a Logstash, which is the open source collection engine for pipelining our data into Elastic for real-time processing and analysis. Logstash is very commonly used. You can use it, outside of the ELK stack. You can use part of it. Very common tool. It's used for data normalization, cleanse and parse the data, and then for event enrichment. So if you have disparate log sources that maybe don't fit nicely into a certain type of format, then it'll help you parse those logs so you can get meaningful data out of them, and then not use any data that's not relevant to what you're trying to collect. Kibana is the visualization tool that's used to interface with the Elastic stack. Any user-defined application can also serve this function. So Elastic makes it very easy, via standard REST APIs to just retrieve or push data to the entire stack. So, but Kibana is like the front end if you wanted to have an easier approach to use that. But you can use Kibana for your dashboarding and for your alerting, and then also for capturing events that are relevant for your specific investigation that you're conducting. And so that's a really powerful feature that would be a little bit more difficult to do if you were just going to try to retrieve logs via standard JSON. So this gives you a little bit better way to visualize some of that information. And then beats, those are open source data shippers or agents that can collect and send data. So there's a number of different beats that are available. So you have file beat, which is utilized to collect application logs that you're interested in. This can be Nginx logs, MySQL logs, Apache logs, any type of log really. There's also metric beat, which can be used for collecting system and service metrics. Packet beat, which can be used for collecting network data. WinLog beat will collect Windows event logs for you. Heartbeat will give you some uptime metrics, so you can think of that as kind of an alternative to Nagios or SolarWinds if you're using either of those products for uptime statistics. And then Beats by Dre for whenever you want to be listening to some sick bass drops whenever you're configuring all of this. Obviously that last one's a joke, but there is the option to configure your own beats, so you can call them whatever you want. You can develop whatever beat you want and integrate it into this entire platform. So the configuration and the customizability of Elastic makes it a really powerful tool that you can utilize. So some architectural considerations. So Elastic is distributed and horizontally scalable. So the concept is that Elasticsearch is built on nodes, and nodes consolidated develop into your clusters. So a node is an instance of Elasticsearch, and then when you combine everything together, it's a singular cluster that you can utilize. And then you also have the option to expand that horizontally into multiple clusters. So it really just depends on how you want to implement it. And we'll talk a little bit more about clustering later on. Like I had mentioned, Elastic makes it very easy to integrate with via REST APIs. I mean, you can use your own applications, you can use Kibana dev tools, you can use any number of, you can do it from the command line from your host using curl. You can use any number of tools available to communicate with it. So that makes it really powerful. It has support for predefined data retention policies. So we are going to talk a little bit about ILMs and kind of the standard for how those lifecycle management policies are developed. And that again, that's going to come down to what your specific requirements are for data retention. Based on the way that the nodes are configured, you typically have like a hot, warm, and cold tier. And it does take a little bit of latency to query data that's stored in each of those tiers, based on just for the way they're set up for archival purposes. So, and then there's several deployment options available. So on premises, you can configure the entire Elastic stack within your own data center on your own hardware. You can also utilize a service called ECE, so Elastic Cloud for enterprise, I think. And you can just host basically a cloud version of Elastic so that you don't have to do a lot of the manual configuration on the back end. You can, for instance, spin up new data nodes if you need them as part of your cloud offering. And then there is an actual Elastic Cloud offering that basically, abstracts all of that kind of away from you and just lets you focus on the application layer. So it just really depends on how you want to integrate and utilize Elastic for your environment. If you don't have a lot of personnel available, to like monitor and configure Elastic, then you might want to look at one of the cloud offerings, because it does take quite a bit of substantial work to actually keep the stack running from an engineering standpoint, and that's in addition to optimizing your dashboards and optimizing your alerting and things like that. So you really need to have multiple teams kind of dedicated to it. That's also dependent on your data requirements as well. If you work in an environment where you can't necessarily use a cloud vendor to store some of your data, your log data, then obviously you wouldn't be able to make use of their cloud offering. So it just depends on what you need it for. So architectural considerations. So, and this is not like an enterprise version of what you configure to be like an Elastic setup. So don't I guess focus on it too much. I just want to give you like a basic visualization of kind of what it looks like with the different agents and log sources that are coming in. Some can be sent into Logstash if they need to be further parsed in that regard. And if you're running the Elastic agent on your endpoints, Elastic does offer its own agent that'll basically combine all the functionality of those different beats into one standalone executable. And then you can have that pipe data directly into Elastic. It just communicates over port 9200 standard COM port. So, and it can be managed centrally through the Elastic Fleet Server. So you can have Fleet Server manage your agents, and then you can push different policy updates to those agents directly from the Fleet Server. So it's a very centralized and easy to use, intuitive interface to actually manage your agent policies. And then you can develop different policies for different host types as well. So if you're running Windows machines and you want to collect, the Windows logs, you can have the Elastic Agent policy be applied to those machines and then collect Windows specific ones. Same with Mac, same with Linux. So you can configure them based on host operating system, or if you have different use cases for endpoints, you can also make that configuration as well. So it's very easy to customize it through the fleet management server, and that's probably the recommended approach if you're able to do that. If not, then there's always the option to use traditional logging sources and parsing and just piping it directly into Elastic as well. As long as it's formatted in a way that Elastic can understand it, then it will accept anything. So you can send any type of data to Elastic and it'll go ahead and do the indexing for you. So you can see the Kibana machine on the right. That's how you would make modifications to your Elastic cluster as one option. And then you also see the data nodes that you can define. And then you would have different ILM policies, lifecycle management policies that would be applied to each of those tiers. And through the GUI interface and Kibana, you can, it's relatively straightforward. You can set, different data retention policies. So When data first comes in, it goes directly to the hot node and it sits there for 30 days, for example. And then it'll roll over to the warm after 60 days and then 90 days for cold storage. So, you know, you can kind of play with those settings and figure out which one makes sense. But, you know, obviously, if your intent is to do long-term archival of data, then you may want to set that cold policy very high, or you may want to, you know, even have offsite backups from your cold storage tier if you need to retain data for years, for instance, and that will give you kind of a good like data flow of how it goes through the process and cycles through the ILM policies. And then, like I had mentioned, you can also have multiple clusters. So if you have, for instance, multiple sites and you want to kind of distribute the workload, you can set up different clusters. There is the possibility for cross-cluster replication, so you can replicate, you know, events across different clusters if you need to. If not, you can also run separate clusters, and you know, it's typically a good idea to also have like a development cluster so you can actually test some of these configuration changes, or if you're developing custom parsing, it'll be you know, that's generally a good idea so that you can actually make those types of changes without impacting production. But I also, you know, understand that budgets may be limited in certain instances, so you may not always have, you know, the ideal setup. So you kind of got to just work with what you got. But that is an option, and there's built-in features to allow for cross-cluster replication if you need that. So additionally, on architectural considerations, any data source that is shipping logs should be mapped to the Elastic Common schema. So this schema allows you to map your logs to a number of different fields. So for instance, there's a client field, and you can define, you know, client address, IP, MAC address, port numbers. So kind of the standard things that you'd expect to collect from a client on your network. Same with DNS, you know, very similar DNS types of field. HTTP, if you're going to log HTTP events, request method, response bytes. There's you know, basically anything you can collect from an HTTP field, header and body. You can also include. You just need to make sure that it's mapped to what the field expects for the Elastic Common schema. Now, do you have to be completely compliant with ECS? No, you can kind of work around it, but it would be recommended. And you know, because sometimes there isn't a straightforward mapping to a specific ECE field, but you know, in that instance, you kind of just make a best guess. Look at the data type that the ECS field is expecting. So if it's expecting a long, you know, then find a field that maybe kind of sounds like what you're trying to collect, and then, you know, as long as it's a long data type, then you can go ahead and map it to that field. Same with keywords. If it's based on a keyword, just, you know, go ahead and make that guess and integrate that into your mapping. You can also look at the different levels, so core and extended. So core is the set of generalized fields that should be populated where applicable for all ECS compliant implementations. And that's specified in the ECS documentation that's on Elastic website. And then extended would be those non-core ECS fields. So a lot of times the extended levels will get incorporated into core at some point. It just depends on priorities. ECS compliance ensures that the data is well structured and can be searched and aggregated easily. So whenever you're doing a search on your Elastic data, if you're searching by host name or if you're searching by timestamp, then when it returns the results, it'll provide, you know, those taggings that match to the ECS fields, and that just gives you a better understanding of exactly what type of data you're looking at. So identifying log sources. So, you know, Elastic basically lets you define whatever log sources you want to collect. So you should determine what should be collected and prioritize that analysis based on this collection. So like I mentioned, you should leverage, you know, the Elastic agent, the Elastic security agent for easy management of endpoint policies. So Elastic bought Endgame, and so a lot of those types of features that were prevalent in Endgame as a platform for launching investigations and also for endpoint protection are being integrated into the Elastic security agent. So it's actually looking very similar in terms of a product offering, which you can kind of expect when someone gets acquired. Allows you to build specific policies for host types deployed in your environment. So I had already kind of mentioned that before. If you have any disparate hosts, you can define your own policies through the fleet manager. And yeah, these can be defined and applied through a management fleet agent policies in the Kibana dashboard. And you can collect a number of different types of logs. So like I had mentioned, you can do system monitoring events. So some things like syslog and auth logs, and then specific Windows security events, you can collect those. Perfmon, you can collect performance monitoring logs. And you can also modify configurations on your specific Beats implementations if you're utilizing Beats. So that's another option as well if you're not specifically using the Elastic agent in your environment, or if it's not universally applied. So for threat hunting, we are interested in the attack vectors mapped to our threat model in addition to detection and prevention of lateral network movement. So when you design, when you're designing applications used internally, or even when you're interfacing your applications with outside vendors, a lot of times you're going to build that threat model at the application level, but you want to start thinking more broadly than that too, right? You want to make sure that you have a threat model for your network and that it's correlated to any threat intelligence that you have. For instance, if you know that there's active threat actors out there that are specifically targeting your industry, and you receive open source intelligence that they are utilizing an avenue that is part of a product offering that you support, then you need to make sure that's kind of mapped out into your threat model. So when we want to think more broadly than just at the application level, we also want to think about the network level as well. So when we're thinking about it like that, we need to start thinking about the way that an attacker would enter the network. So endpoint logs, firewall logs, email logs are all going to be primary focus areas for this initial attack vector. And there's other log sources as well, but think about the most likely scenario of how someone would actually get onto your network. So logging data from your DMZ should be a priority as well to identify entries. So if you have any public-facing systems, you got to expect that that's going to be a primary target of opportunity. So those need to be locked down, but they also need to be logged. You need to make sure you're collecting logs on each of those devices. And anything that's end user facing as well should be prioritized, since phishing emails are like a primary avenue of getting malicious software onto your network. So start from the outside and work your way in. So compromised endpoints communicate with network shares, for instance, internal web applications, DHCP servers, any number of applications. So once you've identified those entry points onto the network, then assuming that one of those gets compromised, what else does that device or that host have access to? What else does that user have access to? And then once you identify that full attack vector where you have the entry point on the network going through the host machine, and then the pivot points, you can kind of start to outline that full attack vector from entry to some of your critical applications, the things you're really trying to protect on the inside of your network. And that's all developed from this hypothetical initial compromise to critical application. So based on that, assign probabilities and start developing alert levels and categorization. So this is the type of thinking that needs to go into designing a product like Elastic, or a solution like Elastic for your log monitoring and for your threat hunting platform. Start determining which logs are really prioritized or really critical to you, and then prioritize those. And then obviously, if you can identify that full attack vector, then you need to establish some technical and probably administrative security controls for mitigation. But those are never foolproof, right? There's always a way. There's always a firewall that hasn't gotten the most appropriate policies put in place, or there's always an end user that does something dumb, or there's always an administrator that makes a mistake and leaves a configuration wide open. So we need to account for that, and that's why logging in a SIEM is so important to your environment. So once you've identified this path, just log everything in this attack path. It can get overwhelming, so a small to medium-sized organization if they're logging as much data as they possibly can, their environment will probably have on the order of tens of billions of documents that are indexed, and for corporate environments, hundreds of billions. And if anyone has any more than that, if anyone's up in the trillions of documents range, just mention that after the talk is done. That'd be interesting. That's a lot of data to go through. But that's why it's better to have it than to not have it. So for threat hunting, Kibana supports the concept of pivoting. So that's where you can connect your events to a specific timeline. Those events of interest that you've identified as part of your log analysis, and based on any alerting that you've received, using observations to target your threat hunting effort, and then defining detection and logic. So in the security app in Kibana, there's a tab where we can start run through an investigation. We can go into the alert view and the resolver to follow the execution of a particular event. In all honesty, this looks very, very similar to Endgame if you've used that. So it'll build out the execution of events that respond from a particular process that was flagged. And this can be, from your endpoint protection or from any alerting events that you've set up. But it'll track it through API calls that process is made, files read, new processes spawned. So you can see, like a visual timeline of the way that process has been executing on that host. And then as part of your investigation, you can save the associated log events to collect in timeline. So there's options and tabs in Elastic to build out timelines, and then you can also add those timelines and any other pertinent information to your investigation in a case. So you can there's an option to develop a case in Elastic and collect all your notes relevant to that investigation, and then you can make sure that everything's centralized in a specific location if you need to use it for reporting later on. So Elastic also supports the integration of threat intelligence modules. So there's a number of very commonly used websites that you can pull information from, and then you can modify in your configuration to go ahead and use their API endpoints to use those as reference for threat intelligence. And that can show up in your observation feed just as easily as any other data. That'll allow you to do a little bit more of that correlation based on any threat intelligence that's kind of built into the feature. And that's a great addition to any other avenues of threat intelligence that you have. So, if you're a member of FBI InfraGard, if you're monitoring, Dell, X-Force, or anyone else that has threat intelligence, they release them. It's a great way to correlate not only the technical real-time intelligence you can get, built in with Elastic, but also just what you get through open source and public channels. So like I mentioned before, whenever you're doing new data ingestion of new sources, they do need to be mapped to Elastic Common Schema. So, and this is just an example of different fields that you can be mapped to within the ECS. So there's more information on this on their website. I would recommend, if you're really trying to build out this product and make it as efficient as possible, you're going to be spending a lot of time looking at ECS. It's a whole book. All right, so with this, you can gather artifacts from an event once it's been identified, and then you can use that artifact. This is continuing on with our threat hunting piece. So once you've identified an event, you gather the artifacts and then use them as your pivot point once you have determined that further investigation is required. So if you have any file hashes of the event, if that process was flagged, you can collect the file hash. You can look at host names that were affected by this particular malware, for example. You can look at the timestamps for when that event occurred and any other relevant information for correlation. And then what you can do is you can go in to your index patterns and you can add these file hashes as part of those, and that'll help you identify other compromised hosts. So that's really kind of where you'd implement, the real threat hunting that you can do with Elastic is being able to identify an event, having a good enough solution at the beginning to where it'll alert you to, you know, event going on, and then you can take that information and plug it back in and do a wider search of your network through index patterns or through just manual data searching. But that's, depending on the size of your network, that could be cumbersome. So you really want to try to leverage any information you get from the initial infection point. That'll make your searching a little bit easier. And once these expanded indices and alerting rules are implemented, and then you can build them out into dashboards for easier observation. So if you have a list of hosts that were alerted, then you can go ahead and just identify all those hosts in your dashboard, go through the GUI interface and just, you know, click on each of those hosts and the specific logs, events that were correlated in Elastic, and then you can just go ahead and graph that. And it makes it really easy to visualize versus trying to collect all this information through JSON. And lastly, Elastic does provide machine learning integrations. So, you know, this provides the ability to analyze data and be alerted to specific events. It does require a platinum license through Elastic. So, unfortunately, if you're, you know, downloading the free open source version, you're not going to be able to use their specific ML integrations. But if you are a corporate customer and you have that, then you can obviously utilize those. But it'll be set up, and they should be set up and run as separate ML nodes in your cluster. And that's just for resource purposes, because it makes use of the remaining RAM that's in your JVM heap whenever Elastic is running. So it supports both unsupervised and supervised ML subtypes. And this is, you know, which avenue you choose kind of depends on you know, how many folks you have available to actually fine tune those. So, you know, preferably you would probably have a better understanding of your environment, and so you can kind of work with those models in a supervised mode to continuously tweak them. But if you can't, then unsupervised might give you a baseline as well, and it'll operate off that baseline. So it depends on how well you know your environment. And once you get your cluster up and running and it's been going for a while, that's something that you really need to be focused on is understanding what data is coming in, what data is expected, you know, on a daily, hourly, weekly basis, and then making sure that there's that the initial alerting is in place so you can actually flag on events that are interesting. So recommended after establishing your architecture and identify data sources. So again, when you have enough data for a baseline, that's when you should really be focused on building this out. All right, so we're going to wrap up. Just indexing and searching your data is pointless if your goal is to utilize Elastic for security operations. You really need to have a good alerting policies in place. You need to identify, you know, if a host is acting a certain way, you know, that needs to be an alert, or if a user is acting a certain way. You need to make sure that that's all built into your Elastic features. Establish your alerting levels and spend time fine tuning so you don't overwhelm analysts. So that's, you know, a common complaint that SOC analysts have is they're getting too much data and they don't have time to look at it all. So on the engineering side, that's where you got to really fine tune it and make sure that you're only alerting on things that should actually be looked at. Make use of the threat intelligence models that are included, or define your own if you want to use different sources than the ones that were included there. You know, you have the ability to do that. So it's a great feature to use. Consider integrated data analytics and machine learning if you have the ability to. If you don't have the ability to use their paid offering, then, you know, you can run your own analytics. There's no reason why you can't develop something to do that for you. Recommended develop a test cluster that can be leveraged for implementing new detection rules. And then lastly, exercise. Run exercises. Use dummy data and dummy alerts on your actual rule sets and see if they alert the way they're supposed to. Make sure your SOC analysts are responding appropriately. Make sure your incident responders are executing appropriately. So make sure you run through that at least on an annual basis. So it's the end of the presentation. Are there any questions at this time?
I have a question.
Yes,
What in your opinion is the most challenging part of using the Elastic stack in a SOC environment?
Definitely, definitely setting it up. You know, once you have it set up and you have the baseline understood, it's a lot easier to use. But if you're developing it on-prem or if you're using the ECE option, you got to manage all that infrastructure yourself, and you've got to define the policies. You got to make sure you have, you know, the physical resources to do that. So that's the most challenging part. And then once it's built out, it's a little bit easier. But you know, that's the same challenge that exists with a lot of different SIEM platforms. Is, you know, you're going through a lot of data, and so the fine tuning of the actual alerting is always going to be difficult. But it's why you got to spend so much time on it. That's the whole point of the SIEM, is to make sure you can get alerts properly. So yeah, the setting up is definitely the biggest one.
Thank you.
Have you worked with an organization that uses the machine learning features? So I haven't. I don't know if anyone else can talk more about the machine learning features for Elastic. I have not worked with an organization that uses it.
Any other questions? All right. Well, thank you very much, JT. That was pretty awesome. Now I'm gonna set up Mehdi as presenter, and we can continue.
Yeah, please go. Okay, looks like we're good. Just I unfortunately only have one screen. That makes things kind of difficult, but we'll get it. We'll get it working.
It's all right.
Okay. And y'all don't see the junk on the side of the screen with like the chat and everything, do you?
I see your camera and I see the entire of the slide, so you're good to go.
Okay. Okay. All right. Well, thanks for having me. JT invited me to round off the second hour of the meeting. This is my first event with this organization. I appreciate the invite. I was in Miami not too long ago for Miami Hack Week, so I had a great time. It was pretty crazy, and I'm here in Louisville, Kentucky. And if there's probably only one day of the year where Louisville might get a little crazier than Miami, and that just happens to be today for the Kentucky Derby. But I'm safely in the house because I don't have any friends, and we're gonna talk about some security. So my name is Mehdi Sabrawi. I'm a research engineer at Tenable. Given that this is a security-focused crowd, maybe some of you have heard of Tenable or the Nessus Vulnerability Scanner or Tenable.sc or Tenable.io. I got my doctorate from the University of Louisville in computer science and engineering, and that is not my real face. So what we're talking about today is formal methods, and specifically TLA+. Formal methods is kind of, it's been around for a while in like the academic scene. I have not seen a whole lot of mention of it like in the security sector. There is, if you're talking about like getting deep into kernels and kernel security and things like that, there's some formal methods in there. But as far as like security practitioners, it's not usually on their radar. So hopefully with this talk, I can introduce you to some tools and some ways that maybe you could incorporate a little bit of formal methods, specifically TLA plus and model checking into your day-to-day, maybe get some value out of it without having to go to school for 10 years to figure out what the hell is going on. So we're gonna talk about when, what, why you might use formal methods and the two different types that I'm most familiar with, theorem proving and model checking, and then the TLA plus specification language. So given that you're all security professionals or at least enthusiasts, I'm sure you're very familiar with a bunch of very important systems getting hacked. There's probably Teslas all over Miami. and other, actually you don't even need a Tesla anymore. Like every car is fly-by-wire and probably connects to the internet. But you have cars, phones, laptops, systems inside of your own body that might be open to getting attacked, to getting hacked. And these are very important systems that need a whole lot of our scrutiny to make sure that they're safe. I should have said secure. Safety and security are very related. We're very familiar with security here, but safety is tightly correlated. And with a lot of these systems, pacemakers and cars specifically, we also need to think a little bit about safety. When an attacker attacks like an e-commerce website, they steal money. When they attack a car, it's possible that they could steal lives. So the stakes could be higher depending on your perspective, but they're still very important. What we would like is strong guarantees about these very critical systems. Just as an example, in a car, we cannot get control of the brakes via the audio system. And we know that this specific guarantee, a property of the system, is not guaranteed in most cars today. We have many examples. I'm sure you've seen the stories out of DEF CON and other security conferences of people inserting a CD into a Jeep and then just taking full control from there and being able to drive it around and shut it off and disable the brakes, etc. What we would like to do is guarantee that even if the audio system is compromised, we can't get to the brakes or other things. For a laptop, as an example, we might want to guarantee that top secret information, however we define that, can't flow out to the internet. Formal methods can help us with these strong guarantees. And when I say guarantee, I mean mathematically proven, or we verified it. We have proof that this system holds this property. So we have some ways to make our systems more robust and more secure. I'm sure you are all familiar with testing. You've all probably worked with unit tests, or just maybe you have a QA department that just tests things and throws things back to you when things go wrong. There's also process certification. Boeing is a very big example of process certification and how that might go wrong with their, I think it's the 777 MAX that they had a lot of problem with the past few years. That plane goes through a crap load of process certification, all of their planes do, and they still run into problems. And then there's formal verification, where we have proven guarantees about the system. I don't want to like say that I'm sure that Boeing uses formal verification and they still run into these problems. It's not the end to all of our security problems as professionals, but it's another tool in the toolbox, and it might be able to satisfy some things that we had trouble rectifying in the past. So we've all done formal verification. We've done proofs in geometry and calculus, and there's an example of a proof right there for an isosceles triangle. We might come back to that in a little bit. So why can't we do it in computer science? A big idea here is that we want to make models, and then we want to really think about these models. We want to reason on these models and make proofs on these models, given properties of the system and rules and things like that. We can prove certain things about the system. An important part of making a model is our assumptions. The models are not reality. They never will be. They never will be that complex. So we have to understand not only what the system we're modeling, what it does, and what is important for us to capture in our model. We have to understand what assumptions we are making. That distance and the assumptions are basically the distance from the model to real life. Because we want to make our model as simple as possible so that our tiny human brains can think about it, but no simpler, because we want it to be able to do actual work and mean real things. As far as what properties we might want to verify with our models, we have pretty easy properties, like there's no division by zero in this software. That can be accomplished with static analysis, all the way up through full functional correctness, which is all possible behaviors that we have in our design are expected from our live system. And I guess I should say that I borrowed these slides from a presentation on SEL4, which happens to be a fully verified microkernel. That's beyond the scope of this presentation, but if you're interested in full verification and all of the time and effort that takes, you might look up the SEL4 microkernel. So the strong guarantees. Okay, so to wrap that up, we need strong guarantees. We want a small gap from the model that we're reasoning on to reality. And we want our model to capture very strong security or safety properties. And these all go into how we pick what's important about the system that we need to model. One trick to doing this is to start very, very simply. And then as you verify certain aspects about your simple model, you refine it and it gets more and more complex. And then you can verify that your security properties still hold as your model grows in complexity. So there are some challenges here with proof engineering or with modeling. For one thing, with proof engineering specifically, is that it's all or nothing. You either prove that you can't get to the brakes from the audio system in your car, or you don't. You can't half prove it. You can't prove that, oh, it's difficult. You either prove it or you don't, and there's no guarantee that what you're trying to prove even can be proven. I guess that's part of number two there. That is hard to predict. You don't know from the start whether what you're doing is possible. The next thing is order of magnitude. It could take forever to prove what you're trying to prove. It could be possible, but it could take 16 sun deaths for your laptop to crunch through all the numbers and all the possibilities to find the proof. On the positive side of that, once you've found the proof, it's very easy to verify that the proof works, but it can be very difficult to find the proof. And then we have the level of abstraction. If your model doesn't accurately capture reality, then it's not of much use. So some types of verification, there's theorem proving, where you have theorems and lemmas and assumptions, and then you have basically these building blocks, and then you build something out of all of these theorems. And then you have model checking, which we're going to dive into today, where you have states, transitions, a beginning state and an end state, and then you have a mechanized model checker that can run through all your states, run through all your transitions, and show you where your properties might be violated, where your security properties might be violated. So just as an example of theorem proving, the isosceles triangle, we know that the two sides there of an isosceles triangle are the same length. So what we might want to do with that assumption is show that angle B and angle C there are the same degree. So that's an example of assumptions, what's given, and something that we might like to prove. For math, obviously it gets more complex than this for real world systems. I'm not going to go through this because frankly, I didn't practice it and I don't understand it and I don't care. So we'll just move on. So here's an example of model checking. The big circles there, you see S0, S1, and S2. Those are the states. These are the states that your program, if you're a programmer, or your system, if you're a systems designer or an architect or a systems analyst, these are the states that your system can be in. If you're a programmer, these are the values that your variables could have. If you're a systems designer, in the SIEM example that from JT, maybe it's possible that one of your agents has detected an anomaly. That could be a state. Either it's flagged or it's not flagged. Those are two different states. And then you see the arrows in between them. Those are the transition rules. This is how you transition from one state to the next. So in the SIEM example, if the agent detects something that's anomalous, that's a rule. Detect something anomalous, move to the next state where I'm flagging this behavior, this packet that I see on the network. If the analyst decides that no, this is no big deal, we can ignore it, that's another transition rule to go back to the original state that I'm not flagged. I'm not pointing anything out. Nothing's wrong. So some problems. Verification is very hard with model checking. It's very easy to design a system that's too complex, and then you run into the state explosion problem. The more complex your model, the more states, and then checking it becomes an exponential problem. And you very quickly run out of time, very quickly run out of memory and patience. And with theorem proving, there can be an infinite number of layers. You have no idea if what you're trying to prove is even possible to prove. That's part of the satisfiability down there. That's an NP complete problem. It's very difficult. So verification is not for everyone. And this is where we come into when not to use modeling or TLA plus. If your budget is constrained, this is probably something that you cut off. If you're a lean startup and you're trying to get your product out, minimum viable product, maybe modeling is not where you're trying to go right now. You're just trying to get it out the door. It's not a good use of your time. If your system is not important, I mean, and this is relative. Obviously, a mission critical system is important, but maybe modeling is not good for it because it's a lot of tiny components and failure is handled very nicely. And the example of the Nessus scanner, like we have a lot of plugins and we don't necessarily model each plugin because if a plugin fails, we have a way that it fails gracefully and it doesn't bring the whole system down, etc. Like we try to get those plugins out the door. We don't need to spend time with TLA plus and modeling each plugin. If your system is pretty cookie cutter, like you're just running a website, e-commerce website, simple, or you're an IT guy or IT person and you're trying to set up VPN access for all your remote users, that's a system it's been done so many times before. You have a reasonable expectation that it's going to work well. You're not doing anything novel or unique or silly. And your standard tools work. I mean, your OWASP 10, it's great. The vuln assessment tools like the Nessus scanner, they're great. The standard testing protocols that you might have, your QA department, those things work great. And if you're, the last thing here is if you're trying to test very specific things or implementations, if you're trying to test like the mappy parts of this new cryptographic system that you're working on, with like specific numbers and formulas, maybe model checking is not for you. There's probably a way to do it that's beyond me. But when I think about that stuff, I don't think about model checking. I think more about feature improving. Let's talk about when to use TLA plus in modeling. If your system is absolutely critical. We had the car example before, even though some of these companies don't consider cars to be critical. I'm sitting in a car and if it crashes, my life is over. I consider that critical. Things like critical infrastructure, the dam sector, electrical grids, things like that, where real catastrophe could happen if something goes wrong. That's a case where you might want to, throw some more money at it and get a model going and prove to yourself and prove to whoever the leaders are in your organization that what you're doing works and is correct. If you're building a system from the ground up and you're not sure if what you're trying to do is possible, then maybe modeling is a good option. You model the system first. That forces you to think about it, and you might find, even without the proof for the verification or the checking, just writing your thoughts down and converting your thoughts from an informal napkin math sort of drawing to a formal model helps you catch a lot of issues with it without even having to run the model checker. Another case is when you're dealing with very specific curveballs to existing systems. I'm sure a lot of you have dealt with the scenario where the founder or CEO of your organization, they want special permission, they want a special account. Your database is encrypted and it has all of these rules for encryption, but the CEO, for whatever reason, they want to be able to like read everything. So when they look at the database, they want it all to be unencrypted just for them, but for nobody else, and that's like a different type of account with different rules. You want to make sure that just the existence of this account doesn't break all the security for all the other accounts. These sorts of things. Yeah, modeling might be this might be something to model. You might want to make sure that what the CEO is asking for doesn't break everything for everybody else. So it could be good to have some proof to show that this works. Alternatively, it could be good to have some proof to show that this doesn't work, so you could throw the request back into their face. Tell them to pound sand. And then finally, highly concurrent systems with simple components. And this is what TLA Plus was built for. And this is what all the biggest companies that use TLA Plus use it for. An example would be a central server with many agents that all interact with the server, that interact with each other, that maybe they do simple jobs, but the whole system itself can get really complex when it's all working together. If you have 1,000 agents or something like that, that can quickly grow beyond the space of a single human mind to keep all in your head. And modeling this might be very helpful. Like, how do you find a deadlock? with 1,000 agents and 6 different master servers, for example. It's very difficult. I can't do that. Modeling in TLA Plus specifically can help with that. And these are examples of the companies that that use TLA Plus, that use, I think HackMiami just uses SEL4, but Amazon Web Service, Cosmos DB was built on top of, that's a Microsoft, they call it Planet Scale database. I don't know what that means, but TLA Plus was developed by Leslie Lamport, and he works with Microsoft, and this project was started and built using TLA Plus. NRIA is a national lab in France. Carnegie Mellon University, they all use TLA Plus or some form of formal methods for their critical systems. So TLA Plus stands for Temporal Logic of Actions. It's a formal modeling language, a formal specification language developed by Dr. Leslie Lamport. I don't know if he's at Microsoft or he just works with Microsoft. I'm not certain how that works, but anyway, it's a very mathy sort of tool. It uses a lot of mathematical notation, logical notation, which some of you might be familiar with, some of you might not be. If you are a programmer, then there is an addition to it called PlusCal, which is an algorithm language, which kind of makes TLA Plus look like a programming language and might be more familiar to you. That's what I use. That's what I'm better with. So we model our system, then how do we know what to check for? How do we use it? What are we using this for? One of the types of properties that we have at our disposal is invariant. And these are properties that are true for every state of your system. A simple example would be if you're trying to design a banking system from the ground up, or some shitcoin from the ground up. Just an example property might be like, for all bank accounts, the balance in each account is never negative. Maybe it's not a realistic property, but this is a property just for example. How we would write this in TLA Plus would be for all accounts that upside down A is the logical symbol for all. There exist for all accounts that are elements of the group of accounts, the account balance is always greater than or equal to 0. So this is something that can be mechanically checked by the TLA, by TLC, which is the model checker. That in every state of our banking system, no account ever goes into negative balance. Another thing is, if the sun is shining, then it is not cloudy, and this is written simply as, if sunny equals true, then cloudy equals false. Now this can be useful for security properties that should never change depending on, regardless of the state that your system finds itself in. For a little networking device, this could be a malformed packet is never sent out of the serial port. So your little device is never generating bad packets and causing problems for other things on the network. The second type is liveness properties, or temporal properties. And these are properties that will eventually be true. So we have our system, it's in its initial state right when you turn it on, push the power button or double click the exe or whatever, it's in its initial state. And all of your invariant properties are satisfied in its initial state, everything's fine, nothing's broken. It's possible that your system may never leave its initial state. And if that happens, then your system's not doing anything. It might be secure, but it's not doing anything useful. So we want liveness properties to prove that our system is doing work. An example of this is a binary ticking clock that alternates between 0 and 1. A liveness property might be, if the clock is currently 1, it will eventually be 0. It will reach a state where the clock is 0. And this is written simply as this, or not simply, depending, but clock equals 1, then that little squiggly arrow, clock equals 0. An example of a more complex liveness property is, if a well-formed message is received in our little networking device, then the signature of the packet will eventually be checked. So we're not deadlocked holding a packet that other people are depending on. We'll eventually check it, we'll eventually send it on its way. Here's an example, little movie that we'll just watch.
Hello, Bob. Yeah, just go ahead and grab it. In the car? Man, son, how you supposed to be helping with this? I'm helping. When you gonna start helping? After you get the bomb. Be careful. Don't open. What? You gotta open. It's gonna be all right. Shit! I told you not to open it. See the message. Proximity circuit, so please don't run. Yeah, I got it. We're not gonna run. Now turn this thing off. On the fountain there should be 2 jugs. You see them? A 5-gallon and a 3-gallon. Fill one of the jugs with exactly 4 gallons of water and place it on the scale, and the timer will stop. Must be precise. 1 ounce or more or less will result in detonation. If you're still alive in 5 minutes, we'll speak. Wait a second. I don't get it. You get it? No. Get the jugs. Obviously, we can't fill the 3-gallon jug with 4 gallons of water, right? Obviously. All right, I know. There we go. Let's fill the 3-gallon jug exactly to the top, right? Okay, now pour that 3 gallons into the 5-gallon jug. It's exactly 3 gallons in the 5-gallon jug, right? Right. Good boy. 3-gallon jug. So that a third of the way up. No, he said be precise. Exactly 4 gallons. Shit! We got less than a minute. Throw this thing away. Look, we can't take it off and it'll detonate. Just wait a second. I got it. Exactly 2 gallons in here, right? Right. Leaving exactly 1 gallon of empty space, right? Yeah. Full 5 gallons here, right? You pour 1 gallon out of 5 gallons into exactly 4 gallons. Yeah. Put it in there. Come on. Don't spill it. Good. Okay. 4 gallons. Good deal, McLean. Put it on his back. Put it down.
Okay, so this little scenario brought to you by the movie Die Hard 3. If you ever find yourself in this scenario, if your first reaction is I better grab my laptop and fire up TLA Plus, then you're correct, because TLA Plus can help you disarm this bomb and figure out how to find 4 gallons of water, how to fill a jug with 4 gallons of water given only a 3-gallon jug and a 5-gallon jug. So let's see how TLA Plus might help us with this. Oops, I don't want to watch it again. I know it's great. So we want to understand the problem in our system a little better. So we have two jugs here. We have a 5-gallon jug and a 3-gallon jug. And we have some actions that we can take. We can fill up the 3-gallon jug with the faucet, or we can fill up the 5-gallon jug. We can dump either jug out, or we could pour 1 jug into another jug. So we have our system, we have the actions that can transition our system from state to state. So let's define this a little more formally. So what are our variables? We have big and small there, those stand for the jugs. And type OK down there is an invariant property, is one of those invariant properties. So type OK is, we want to make sure that in no state that our system could find itself in, the small jug contains more than 3 gallons and the big jug contains more than 5 gallons, or less than 0, because that doesn't make any sense. So we already have an invariant, we already have the variables of our system, just the jugs. So now we want to figure out what are the steps that our system could take. Oh, I should say we should start with the initial state. So the initial state, both the big jug and the small jug have no water in them. That's the initial state of our system. So this is the next step formula, and this defines all of our transitions that we can go from state to state. So we have states that fill a jug, we have states that empty jugs, we have states that pour 1 jug into another. And here we have some definitions of transitions. A transition rule might be fill the small jug. We have the small jug with whatever amount of water it currently has in it. In the next step, the small jug will be full. It'll have 3 gallons of water in it. And because we're modeling the system, we have to define what every variable will be in every state that we transition from or to. So the second part of the fill small transition rule is that big, the next state, the value of big in the next state will be the same. It'll be big, whatever big was in the current state. Because we're filling the small jug, we're not touching the big jug, so the value in the big jug doesn't change. Similar with fill big. In the next state, the big jug will have 5 gallons of water in it, and the small jug will have whatever it had in before. And we have similar rules for empty the small jug, for empty small and empty big. This one's a little more complex. This is the transition rule for pouring the small jug into the big jug. If the amount of water in the big jug and the small jug, if big, let's see if I can get the mouse here. So if big plus small is less than or equal to 5, then you can just pour the small jug into the big jug. The big jug equals big plus small, and small jug equals 0 because we poured the whole thing into the big jug. If, on the other hand, there's more than 5 gallons in both jugs combined, this produces a little loop because we won't be able to fit more than 5 gallons in the big jug. And this, in the example, was left to the reader. So we can go through. Here's the example of big to small with the little loop in there. So if there's more than 3 gallons of water total across the 2 jugs, and you try to pour the big into the small, you're going to be left over with some amount of water in the bigger jug because it wouldn't all fit into the small jug. So that's a transition rule. And here is our model checking results. So we built out these states, the small jug and the big jug. We designated our initial state. Both jugs are empty. We designate our transition rules, emptying the jugs, filling the jugs, pouring one into the other. And it's important to note that these are atomic. So we can't, we move from state to state. There's no in-between states. There's no like the jug is halfway empty because we're pouring it out or anything like that. No, it's atomic. So once we decide to pour it out, it's poured out. And we can run our model checker, and this is just the results of just running the checker with no invariants other than the type OK invariant we discussed before. So let's make an invariant that does something useful. So we want to find out how to get 4 gallons of water in the big jug. The way we do this is by this invariant you see right here. We want to find a state where big, we want to make sure that, and this is kind of counterintuitive with how this works, because model checking can only tell us things that go wrong. So we want our invariant should be big never equals 4. So if we find yourself in a state where there are 4 gallons of water in the big jug, TLC will flag us and will let us know something is wrong, and we have 4 gallons of water in the big jug. So this allows us to run our checker, and what do you know, TLC does happen to find a state where there's 4 gallons in the big jug, so it flags like, oh, something went wrong. And a very useful thing here is it showed us exactly how it got from the initial state where both jugs were empty to the state where there's 4 gallons in the big jug. It shows us every step of the way. In this state, you fill the big jug with 5 gallons, and then down here, you pour the big jug into the small jug. And then up here in the next one, let's see, what is it? You pour the small jug out, then, what is it? I'm blanking during the presentation, but these are the steps that you need to get to 4 gallons in the big jug. Now, I don't know if there's multiple ways to do this. Obviously, the fact that the model checker found this specific sequence of actions, I don't quite understand why it's this solution it found and not another one, for example, but it did find a solution, and this will save our heroes. So it's important to note that model checking checks for bad things. So you model your system, you figure out what state you do not want to reach, you figure out what invariants or liveness properties you do not want to violate, and then the checker can show you what's wrong. Did you reach a state where these invariants are violated? So we wanted to show how to fill a jug with 4 gallons. Our invariant was the big jug doesn't have 4 gallons in it, and then the checker showed us how this was violated. when designing your system, you want your invariants to be things that should not be violated. When you're designing your cryptography system, your IT system, you want to design your invariants so that the model checker can show you where things go wrong, where passwords are leaked out, where data at rest is no longer encrypted. So an invariant might be this data is always encrypted at rest. Can it reach a state where it's no longer encrypted? That's an example of an invariant that you want to design. Now there are some limitations to this. George Box was a statistician, and in the 70s, this is the first use of this example. You've probably heard it before when people talk about statistical models for all kinds of things. Every model is wrong. Some models are useful. That basic idea predated George Box, but he's the first guy who put it into an academic paper. And per his words, since all models are wrong, the scientist cannot obtain a correct one by excessive elaboration. So your model is wrong no matter how cleverly you design it. And there's no amount of adding to the model and making it more complex that will make it perfectly resemble the real life system that you're trying to model. And paradoxically, the more complexity you add, the worse that your model gets. And in his quote, just as the ability to devise a simple but evocative model is the signature of a great scientist, so over-elaboration and over-parameterization is often the mark of mediocrity. So the more complex that your model is, the harder it is to check, and the more likely it is that your model has errors in it that you can't detect because you spent all of your cleverness designing it, that you don't have any cleverness left over to figure out what's wrong with it. And you have to, per George Box here, you have to be worryingly selective. Since all models are wrong, the scientist must be alert to what is importantly wrong. It is inappropriate to be concerned about mice when there are tigers abroad. So you have this understanding that your model does not fully model your real world system. You have to understand what's important and try to make sure that your model captures those things. You want to make sure that it captures where the data in your system is encrypted and where it might not be encrypted. Those are important to you as a security professional. You want to make sure there's no deadlocks in your system. So you want to model just enough so that you might be able to capture a deadlock and no further. That might be important to you as a systems designer. This is specifically for TLC and model checking. The state space of your model could explode. This is where I was talking about before, where you just run out of time, you run out of memory to check every state, to check every invariant property or liveness property. It could be possible that your number of states is infinite, and so it's just impossible to check. And it's possible just from encountering these problems that maybe your system has a problem with it that the model checker can't really tell you about what's specifically wrong, but it's just an indication that something might be wrong. If the state explodes too much, you might need to reduce the size of your model, reduce the complexity, stop worrying about the mice and only worry about the tigers. You might need to rethink your model, what's important, or you might need to rethink your whole system in general, because maybe it's the inability to model it or the inability to check it is signs of bigger problems. So let's see. I think, yep, that's all I have for you today about TLA Plus. There's a link down there at the bottom to get the TLA Plus toolbox, which includes I guess not the software development kit, the linter and everything. The programming tools, it includes the model checker, it includes it also has a TLA Plus proof system, as well as many videos, tutorials, and guides. And I would recommend, if you even want to dabble in TLA Plus for your new system, your new startup, or a system that exists that you're trying to add some reliability and assurance to, that would be the first place to start. I think that TLA Plus, personally, in my experience, is a very gentle introduction into formal methods more generally. So if you're just trying to dabble in formal methods, add some good assurance to your system without losing your mind, this is a good place to start. So any questions?
Is there, here's a question. Is there any specific, I guess, any examples you can give us of something that is, maybe somebody has done some sort of a framework that implements this on against specific threat vectors?
Against specific threat. So I do have a toy project. Let me unshare my screen for a second just to make sure. How do I do this? Is it? Yeah, and then I'll share again in a moment. A little toy project that I personally used for the concurrency. Bring this up real quick. Yeah, so I was talking a little bit in the talk about a little networking device, little toy device. It was part of my research at the University of Louisville. Let me bring this up real quick. Where's the share screen? Here we go. Okay, so this is just an example, a little toy networking device that I modeled using TLA Plus, and this is just a bump in the wire. It's for critical infrastructure. So in this specific case, we were using it with water towers as a way to add cryptography to the water tower infrastructure in Louisville that already existed. So we wanted to be able to make sure that the message is going from the tower itself to home base where all the engineers were, was encrypted and was signed so that we could be sure no one was looking at it, no one was tampering with it. And our solution to that was to have a device set up right in the engineer station and another device set up at the tower, and basically just they called it a bump in the wire, where the system itself would have no idea that these devices were there. They would just send it over the network. This device would intercept it, sign the packet, encrypt it, send it off, and then the device on the other end would verify the signature, decrypt it, and make sure it got to where it was supposed to go. There are 4 components. We wanted this to be concurrent so that the protocol checking and the cryptography components there occurred at the same time to try to reduce down latency, even though latency is not really a concern for water towers, but this was, an academic exercise, literally. So in this case, with the TLA Plus model checker, we have our invariants here too. So here are some example invariants of this little system. Is like only messages of an appropriate length ever reach the cryptography component. Only well-formed Modbus messages ever reach the trusted part of the network. Only properly verified Modbus messages ever reach the trusted part of the network. And only properly signed Modbus messages reach the trusted network, so that here we're making sure our cryptographic component was working, that our protocol checking component was working. And these are all invariants that we were able to check and verify, show proof that this system does what we say it was doing using TLA Plus. So there's an example that's on my GitHub. I can pass that to you. I'll probably pass that after the meeting. I might send that to the organizer. So any other questions?
Yeah. Can you use TLA++
Thank
to
you.
say? Can you use TLA++, or would it be a good idea to use it to say balance PvP 1v1 combat in a game?
To balance combat. Yeah, I'm having a hard time answering that question because every system is so unique, and it's up to the clever developer to figure out if their system can be modeled simply enough to be reasoned on.
Well, what if you basically use it to help you reason those things?
To reason about the balance, I think I understand what you're asking. Yeah. So I don't.
Or limit your requirements for the game, or
So that might be possible. One of the things that I had brought up here about like what TLA Plus is not good for. Where is that? Nope. Okay, it's like a very specific implementation. So I don't know. I'm very familiar with World of Warcraft, so I might use that as an example. TLA Plus might be good for like an ability or certain abilities or certain classes that counter each other. What it will probably not be good for is like the tuning number. So if you're in PvP and you're trying to figure out exactly how much damage one player should do to another, that's probably not a good use for TLA plus. But if you're trying to figure out like what abilities or what certain classes can counter each other and what combination of classes might counter another combination of classes, I could see TLA plus you're getting some good use out of that. Obviously, it's up to the cleverness of the specifiers to write the specification, but I think that's a good candidate. Yeah.
Okay, awesome. Thank you.
Yeah, no problem. Any other questions? If not, I appreciate the opportunity to come talk at you for a while. So if you my email was on there. If you have any other questions, or I'm sure I can pass that to Rod and he can make that available. So thank you very much. Rod, are you around?
Kind of sounded like he was driving.
Oh, okay.
It sounded, I'm not sure.
I don't. This is my first one of the meeting, so I don't know how to end one of these. So maybe we should wait for him, or JT.
This is also one of my first meetings, so.
Maybe he's driving to the in-person event. I'm not sure.
Oh yeah. I wish I could go, but I'm in Louisville. Unfortunately.
Before we wrap here, David, from the person who's co-organizing the social meetup tonight, anybody who's in the area, we're going to head over to Aventura Mall Food Court now. So we'd love to see you. And a big thanks to the presenters for this great info.
Thank you very much. Have fun tonight.
Yes, thank you.
All right. See you guys.
See you.